really solving. I mean, partly because it's quite vague, but it's just motivation. So you have some collection of polynomials and I'm always going to consider the projective case. So these are homogeneous polynomials in n+1 variables, and then we can look at the solution set. So x equals the solution set. Again, consider these as, we only consider the non-trivial solutions, and we consider them up to scaling. So that's in projective space. Pn. And I also have to tell you where I'm working. So I'm working over a field. So K is a field. And then, of course, these FIs are homogeneous polynomials. With coefficients in this field. And then this very general, vague problem is to determine when this solution set has a K point. So when is there a K rational point? So I will talk about integral models, but at the moment, just rational points. When is there a K rational point of X? And again, this is very general, but I just want to point out a few aspects of this problem. So there are two parts of this problem. We could ask for necessary conditions for there to be K rational points, or equivalently, we could ask for obstructions to the existence of K rational points. And then we could also ask for sufficient conditions. So this problem breaks up. We could look for necessary conditions. So we want to know when there aren't points, for instance. And that would sort of, so under this heading, we could have obstructions, like the Brauer-Menin obstruction discussed last week. But actually what I'm going to focus on are sufficient conditions. So we want there to be points, and we want to find some simple hypotheses on X that will guarantee there are points. So this is one way that this problem breaks up. But then a much more important way this problem breaks up is that this really very seriously depends on the field. So this depends. I mean, the nature of this problem depends on the field K. So the kinds of fields that are the most interesting are number fields. But there are many other kinds of fields one can consider. So other types of fields, finite fields, p-adic fields, and then sort of more removed from the original type of field that one would be interested in number theory is function fields over, well, function fields over finite fields. This is also studied a lot, so this isn't so bad. But then what I'm really interested in these lectures are function fields over algebraically closed fields. And so now this is fairly removed from number theory, but the point is that whatever type of question you ask, you could ask it for all of these different kinds of fields. It's always simplest to answer for these kinds of fields. So, I mean, a very important question at this point is, you as number theorists, why should you care about this case, which is the one I'm going to talk about? And largely, it follows from this truism of Tsen-Lang, which you'll hear much more about next week, which is that geometry controls algebra. I mean, this is actually a very geometric question, as I'll explain. And understanding the answer to this question tells you something about the geometry of the problem. And then the hope is that that geometry will lead you to an arithmetic solution over number fields. So it's easier to consider this problem. It will sometimes lead you to theorems over number fields. there's a flip side to that, which is that if you can say something arithmetic, almost certainly you can say something geometric, and algebraic geometers will be interested in this. So number theorists can, help algebraic geometers solve their problems, and so algebraic geometers will love you. All right, so let me also mention, so what kinds of x's am I going to consider? So we saw earlier that the nature of this problem, again, depends very seriously on the geometry of x. So this problem depends on the geometry of x. What do I mean by the geometry of x? Well, we can take x and we can base change from our original field to the algebraic closure. So this, now we're thinking about varieties over an algebraically closed field. So this is the realm of algebraic geometry, and then we can use all the tools that we have at our disposal in algebraic geometry. And the nature of this problem, so for curves, just as an example, for curves, for projective curves, projective smooth curves, we saw that this problem breaks up. There's a trichotomy depending on the genus. So if the arithmetic genus of x is equal to 0, so that means that this base change is isomorphic to P1. And then if the genus is 1, so this is an elliptic curve, the base change. And then finally, the genus is bigger than or equal to 2. So then this is a hyperbolic curve. And the nature of rational points or integral points depends very seriously on which of these three cases you're in. So in this case, you would expect to see lots of points. So maybe not over k, but over a finite extension of k, you'll have a dense set of points. And I mean, that's not even capturing the whole nature of how many points you have. There are lots of points. If you look at the asymptotics of the number of points as the height goes to infinity, then this is qualitatively of a different nature than this case, where there can still be infinitely many points. So after this is after a finite extension, over a finite extension, over L over K. So after a finite extension, L over K, then also in this case there are infinitely many points, but of a qualitatively smaller nature than in this case. And then in this case, frequently, I mean, for instance, if you're working over a number field, there are only finitely many points. So this geometric feature, the arithmetic genus, is implying something about points. I'm going to be focusing on the higher dimensional analog of these guys, of the things that have arithmetic genus 0. Again, it's not as fancy as thinking about those other cases. But if we're looking for sufficient conditions for the existence of points, then probably this is where we should be looking. I mean, and you'll hear much more about the other end of the spectrum next week in Dan Abramovich's talk. So I'm just going to focus on this case. So what is known? I mean, again, this is a very general problem, and it's unreasonable to hope for a single answer, but there are lots of important theorems here. So one of the first is due to Chevalley. And it sort of motivates a lot that comes after it. So it's about finite fields, and I'm mostly interested in function fields over algebraically closed fields, but this is too important not to say. So we're going to consider a single polynomial. Let f be a homogeneous polynomial of degree d in these n plus 1 variables, x0 through xn, defined over a finite field. Fq then what Chevalley proved is that there is always a solution. There's always a non-trivial solution. So Chevalley there is a non-trivial solution as long as the number of variables is larger than or equal to the degree. There is a non-trivial solution if n is bigger than or equal to d. So it doesn't matter what the polynomial is. As long as n is bigger than or equal to d, then there is a solution. And I mean, the proof of this isn't that hard. So you can find the proof written down in a number of places. But just to get some idea of what's going on, maybe sort of a better, I mean, the proof is simple. I mean, what I'm about to suggest is actually as complicated as seeing the proof in every case. But to give you some idea of what's going on that I think probably will have a greater impact than just seeing the proof is prove this when n equals 2, d equals 2 by just counting. What do I mean by that? So we're fixing, so n is 2, so this will be a polynomial in x0, x1, x2, so we'll cut out a subvariety of p2. And then the sorts of equations we're going to look at are degree 2, so homogeneous polynomials of degree 2. So these are parameterized by their variables, and by their coefficients. And there are 6 coefficients considered up to common scaling. So we can consider P2 cross P5, which is just a set of pairs of a point in P2, and then the coefficients, the coefficient vector of some degree 2 polynomial. So what do I mean by this? So aijk, we can consider the x0 to the I, x1 to the j, x2 to the k. And I want that I plus j plus k equals 2. I mean, I'm looking at a degree 2 polynomial here. So to specify this polynomial, of course, it's equivalent to give the coefficients. So we can look at the set of all pairs of a point in P2 and then a polynomial on P2 such that the point is contained in the 0 set of this polynomial. So the polynomial vanishes at the point. So you can consider this. And of course, you can count how many points there are here. Obviously, there are q squared plus q plus 1 points in P2, and q to the 5th plus q to the 4th plus dot, 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 plus q plus 1 points in P5. So we know how many points there are here. But now you can fiber this over P5. We can look at the projection to P5 to the space of conics. And this space has a stratification by the type of conic. So there are a lot of locally closed subsets here. So there's one locally closed subset that parameterizes a conic, a smooth conic with a point. So I'll just diagrammatically indicate that by this. And now, of course, if you have a point, then projection from that point defines an isomorphism of this conic with P1. So the fibers over this point, if I fix one of these points in P5 and ask how many points in P2 cross P5 lie over this point, then there's q plus 1. And then another possibility, we're trying to rule out, is that you have a conic with no points. But I mean, if there were such a thing, then the fiber would have 0 points. And then another possibility is you could have a reducible conic. Well, of course, that always has at least 1 point, the node. But then whether or not it has other points depends on this conic. If this conic, if the 2 tangent lines give a quadratic extension of the number field, of this finite field, then there are no points, in which case the fiber has size 1. And then it could be that both of these things are defined over your finite field, in which case it has 2q plus 1 points. And then finally, it could be a double line, in which case it's, as far as points are concerned, it's just P1. So there are q plus 1 points. So we know the sizes of the fibers over each of these sets. And then we can also count how many double lines there are. Well, to give a double line is the same as to give a line. So there's q squared plus q plus 1 of these. And then et cetera. For each one of these things, you can count how many of these there are, except these two you don't know. So you count how many of these there are times the fiber, plus how many of these there are times the fiber, plus how many of these there are times the fiber. You subtract that from this number. That tells you the sum over all conics with a point times q plus 1, plus conics without a point is equal to that difference. you write it down, and it turns out that there can't be any of these guys. When you divide that number by q plus 1, you already get the set of all conics with a point plus conics without a point. I mean, just the points in P5 minus the points we accounted for from these three guys, and you see, aha, there's a point. So again, the proof in general isn't that hard, but I think this will give a better indication of what's really going on behind these kinds of proofs. It's parameter counting. It's counting, really. And that actually led Tsen to his theorem, parameter counting, which I'll show you the proof of this in just a minute. So Tsen proved the same theorem when you don't have a finite field, but you have the function field of a curve over an algebraically closed field. So same as Chevalley, same conclusion as Chevalley, but now the field K is the function field of a curve over an algebraically closed field rather than a finite field. And let me just indicate the proof, because this is, again, this is one of the morals of doing algebraic geometry as opposed to doing number theory, is that algebraic geometry is much, much simpler than number theory. So this proof, you basically look at this argument and you just write it down almost exactly. The idea is to count, but when you're doing algebraic geometry, you count a little bit differently than in counting, say, over finite fields or counting over number fields. So I'm just going to do the case when our field is the fraction field of P1. So at this point, I'm going to choose an integral model. So this field K is the function field of a curve. And what would be, if you were working with the number field, then you could work with the number field, or you could work with its ring of integers. When you're working with the function field of a curve, you could work with that function field, or you could work with the curve. That's in some sense the analog of the ring of integers. So an integral model, or a projective model is often also what this is called, of K, is P1. So this is really more often called a projective model in algebraic geometry. But this is P1. And now we're considering some polynomial defined over this fraction field. Well, that means that it's a polynomial whose coefficients are rational functions on P1. We can look at the zero set of that inside of P1 cross Pk, P1 cross Pn, and then we can take the closure. So this will give us an integral model of, if we take x to be the zero set, the vanishing locus of this polynomial inside of Pn k, then this is an integral model of that generic fiber. And now we want a height function for points, and the height function will be the degree. So height function. So these are analogs of things that are very familiar from number theory. So in this case, well, I'm sorry, before I get to height functions, I have to say what integral points are here. So integral points, those should correspond to sections of the projection onto the P1 factor. So we have P1 cross Pn. We have just the projection onto P1. So integral point this is just a section. An algebraic section, of course. So it's a morphism. I can say that this is the first factor, but then the first factor has to be the identity. And then the second factor, so let me call that T. And so really it's the same thing as a map from P1 to Pn. So it's a map from, because to specify this section, I want this to be a section of pi, which means that I want this first coordinate of this map to just be the identity on P1, And then, so to give this section is the same as to give this second factor, t. And now, how do I give a map from P1 to Pn? Well, Pn, it's n plus 1 tuples of elements up to scaling, so this map is given by coordinates. I mean, these n plus 1 polynomials on P1, but I only consider it up to scaling. So this is an element inside of the projective space, which technically is something like this on P1. Direct sum n plus 1 times. But let me just say what this is instead of writing down all this nonsense. I mean, it's again these T0, Tn, and I want these to be polynomials, homogeneous polynomials on P1 of some degree. I mean, they're homogeneous, they have some degree. They all have to have the same degree, e. So this integer e, this is the analog of the height. So e is the height. I mean, it's not literally a height. It's just an analog of the notion of a height function. And so now we can ask about how many of these things there are. So given a height, we can count how many solutions there are. In this case, what that really means is we count the dimension of the space of solutions. And we're hoping that it's non-negative. We're hoping there is a solution. That's what Tsen's theorem tells us. So the idea now is to count solutions. Count parameters is what this is usually called in algebraic geometry. It's a parameter count, a classical parameter count argument. So maps from, sections of this map from P1 cross Pn to P1, they're parameterized. I mean, you can specify them by specifying an n plus 1 tuple of polynomials on P1 up to simultaneous scaling. That's why there's that projective space out front. I mean, if I change all of the T0 through Tn by the same non-zero constant, then that doesn't change the map from P1 to Pn. So I mod out by that equivalence. And we ask, how many of these are there? What is the dimension of the space? Well, this is the projective space associated to this vector space. So the dimension of this projective space is 1 less than the dimension of this vector space. So it's just the dimension of this vector space minus 1. We're going to see in a second that all these constants will become irrelevant. But what is the dimension of this vector space? Well, it's n plus 1 times the dimension of degree e polynomials on P1. But of course, I mean, if I choose coordinates x0, x1 on P1, then a basis for the space of polynomials is x0 to the e, x0 to the e minus 1, x1, all the way up to x1 to the e. So this has dimension e plus 1. This is e plus 1. So we get n plus 1, e plus 1, minus 1. So this is the dimension of the space. But that's not what we were looking for. We were looking for sections of script x to P1, of the projection from script x to P1. So now script x sits inside of P1 cross Pn. Let script x, this integral model, it will be, we want its generic fiber to be defined by a single polynomial. So we can choose this to be defined by a single polynomial. So x is the 0 locus of a bihomogeneous polynomial. So we have coordinates here, say x0, x1, and then coordinates here, y0 through yn. So it's a bihomogeneous polynomial, capital F, bihomogeneous of some degree c in x0 and x1, but in y0, yn, we want it to be degree d. So the generic fiber will be, when we think of x1 over x0 as a generator for the fraction field of P1, and then our what I was calling x0 through xn before, that will be this y0 through yn. We want it to be degree d in these variables, so this has to be degree d. So we have this bihomogeneous polynomial, and now when is this section contained in X? So inside of the set of all of these maps from P1 to Pn, which ones actually map into X? I mean, so we have this section to here, to P1 cross Pn, and the question is, what is the condition on T so that the image of S is contained in script X? And the answer is very easy. The condition is that when we plug in T0 through Tn for y0 through yn, that we get a true equation. So the condition is exactly that f of x0, x1. And now we plug in for y0 through yn the coordinates of this map T, T0 through Tn. That this should be identically 0. Now, a priori, this is a polynomial in x0, x1. What's its degree? This is a homogeneous polynomial. So this f was a homogeneous polynomial of by degree cd, which means every monomial has c of the x0, x1s and d of the y0 through yns. But now for each of the y0 through yns, we're plugging in a homogeneous polynomial of degree e. So the total degree of this thing, it's a homogeneous polynomial of degree c plus d times e. So it's c plus d times e in x0, x1. So at least in principle, we could expand this out as a sum I plus j equals c plus de times some c ij. Let me use a because I'm already using c, aij of, and now this will depend on t0 through tn. I mean, what I really mean is it will depend on the coefficients of t0 through tn, but it will depend on t0 through tn, x0 to the I, x1 to the j. And we want that, again, the condition is that this should be identically 0. That means that every one of these coefficients has to be identically 0. If we want this polynomial in x0, x1 to be identically 0, that means we want all the coefficients to be 0. So i.e., want these aij's to all be equal to 0. Now, what are the aij's? Well, first of all, how many of them are there? There's c plus d e plus 1. So the number of coefficients, I mean, the dimension of the space of polynomials of degree c plus de in x0, x1 is, again, c plus de plus 1. So the number of aij's is equal to c plus de plus 1. And each of these aij's is itself a homogeneous polynomial in the t0 through tn of degree d. So each aij is a degree d homogeneous polynomial on this projective space up at the top on this P0, P of H0. You probably can't read this, it's too low. P of H0, P1, O, E. So the dimension of the space was n plus 1, e plus 1 minus 1. And then the dimension of the space of maps to Pn. But what we're actually interested in is the maps to X. And inside of that big projective space, that subset is cut out by this many equations. So what this shows us is that, well, if the number of equations is less than the number of variables, then the 0 set is non-empty. I mean, standard result of a projective space, if you intersect a bunch of hypersurfaces, as long as the number of hypersurfaces is less than or equal to the number of variables, then the intersection is non-empty. So what we conclude is that this set. So therefore, the set of sections S P1 to X of this projection is unempty, provided the number of equations, which is C plus DE plus 1, is less than or equal to the number of variables, which is N plus 1, E plus 1, minus 1. Now let's gather this in about E. So we have N plus 1 copies of E here. We're going to subtract off the D copies of E. So this becomes N plus 1 minus D. E should be bigger than or equal to, and now C plus 1 minus N. So C plus 1 minus N. So this is what we want. Now, who knows? I mean, C could be huge. We started with this rational model, and then we chose an integral model. But when we chose that integral model, we lose control over the degree in C. That degree in the y's, D was fixed, but that integer C was allowed to vary. But as long as this is positive, if this is positive, then when we let the height be large, then this inequality will hold. So if this is positive, then for E very large, this is true. This holds. And therefore, there exists a section, and there exists a section. So this is Tsen's theorem. I mean, there's one tiny, very minor issue here, which is that if I give you an n plus 1 tuple of polynomials on P1, that only defines a map to Pn if there's no common zero of those n plus 1 polynomials. But if there is a common zero, you can factor it out from each of those n plus 1 polynomials. And then what you're left with, I mean, you can factor out the greatest common factor. What you're left with will automatically satisfy the condition. And I mean, also, if you factor out that common factor from T0 through Tn, this will, because this is bihomogeneous, for that new reduced set, I mean, it's sort of like factoring out common factors from the numerator and denominator of a fraction. That new reduced set will still satisfy this condition. So, I mean, you can worry about that, but then you quickly convince yourself that that's not something to worry about. And that's the whole proof. And, I mean, you know, I didn't have to allude to something hard that I'm not going to prove. I mean, this is the nice feature of algebraic geometry. It's easy. And it's so easy that, you know, a number of people, well, I mean, Tsen, although nobody realized this for like 50 years, saw how to generalize this, but quite notably Lang, in his thesis, generalized this. So, in fact, he turned it into a definition, which, you know, at first might sound just kind of excessive, but it's actually very important. I mean, this notion is very important that he introduced. So Lang he turned this theorem into a definition. So Lang, first he introduced a definition. A field K is called C sub R if, so it's a condition very similar to what occurs in the theorem, but a little bit more general. So it's CR if for every homogeneous polynomial f of degree d in n plus 1 variables, I'm sorry, it's CR if every homogeneous polynomial has a non-trivial solution, provided n is bigger than or equal to d to the r. So the r equals 1 case, n is bigger than or equal to d. This is what occurs in Chevalley's theorem and Tsen's theorem. So r equals 1. Chevalley proved finite fields are C1. I need some more chalk. And then for function fields, Tsen proved that function fields are C1. But if you analyze what's going on in this proof, so then Tsen proved function fields of curves over an algebraically closed field. So I apologize. I'll say function fields of curves, and you will almost certainly think of function fields over finite fields, but I mean over algebraically closed fields. But, I mean, again, if you look at what's going on in this proof, then you start with a single polynomial. Now, we could have made this proof work with more than one polynomial. It wasn't really that crucial. Somehow the condition to be contained in each of those hypersurfaces, you can pretend that they're independent, and that will overestimate the number of conditions, but that's all right. If we want to prove there's a solution, we just have to show the number of conditions is less than or equal to the number of variables. So if we overestimate, maybe we could have proved something stronger, but it's not. We'll still prove what we want. And what happened is we started with a single polynomial. When we end up with this, a large number of polynomials, this many polynomials, c plus d, e plus 1, but where each one of them is of degree d, each one of them is a degree d polynomial. And so, yeah, well, I'm not saying this very well, but what Lang observed and also Tsen observed, although again, Tsen proved this in some Chinese journal that because of World War II was lost. And so it took a very long time before, and I mean, then Tsen died, so it took a very long time before people realized that Tsen had actually done this. So this is called the Tsen-Lang theorem. What I am attempting to say, but not managing to get out, is the following. If K is a CR field, let me say little k here, and capital K over little k is a function field of a curve, so is a finitely generated field extension of transcendence degree 1. Then capital K is CR plus 1. I mean, so you could consider this condition where R is equal to 0. Then this condition is that n is bigger than or equal to 1, which is no condition at all. So the R equals 0 case, it says that every polynomial has a solution, which means that your field is algebraically closed. So a C0 field is algebraically closed, and conversely, an algebraically closed field is C0. And then Tsen's theorem says, well, if you have a function field over an algebraically closed field, then K is C1. So that is a particular instance of this. But then you can just keep iterating this, and what you conclude is that sort of same hypotheses, but transcendence degree is equal to R, then if, except I probably already used R, so let me say N, then if little k is CR, then capital K is CR plus N. So in particular, the case that we'll consider most is if capital K over little k, if little k is algebraically closed. So then it's C0. Then capital K is Cn. So the function field of an n-dimensional variety over an algebraically closed field is automatically Cn. So again, you make this definition, CR, which is a very useful way of imagining how you break up fields into classes with similar properties. And then Chevalley's theorem is that finite fields are C1. And then Tsen, and then generalized by Tsen-Lang, is really a theorem about passing to a finitely generated extension, that a finitely generated extension is CR plus 1. That index R goes up by 1. Again, you're demanding, when you go from CR to CR plus 1, you're demanding a stronger hypothesis on the degree. Not just that the degree to the R is less than or equal to n, but the degree to an even higher power is less than or equal to n. So the degree has to be even smaller, and so it's a stronger condition on the polynomials you consider. And so it's a weaker condition on the field. More fields will be CR plus 1 than our CR. Every field, yeah, so let me point this out. CR implies CR plus 1. So an algebraically closed field is obviously C0, C1, every C whatever. A finite field is C1, C2, et cetera, et cetera. So you usually just talk about a field being CR for the smallest value of R for which it's CR. Okay, so why were they considering this? I mean, again, oh, yeah. Okay, so this is a good exercise. So how sharp is this? Yeah, I actually meant to. So there's a notion called normic forms. And this is related to well, I mean, it's just a way of rephrasing your question. So the question, which is a very good question, is this sharp? I mean, could you prove a stronger theorem than this? Maybe it's true that, I mean, maybe it's not true. I mean, it's not true, but I mean, when you look at this theorem, maybe if little k is CR, then also capital K is CR. Why do we have to go from CR to CR plus 1? But the answer is, I mean, if you want something this general, then it is sharp. So is this sharp? Yes. And then the problem is, the exercise is to find examples. Give examples of CR fields K, I mean, one for each R, such that K adjoin T is CR plus 1. And actually, this is, I mean, again, but not CR. I mean, of course, K, but not CR. So, I mean, this is actually kind of interesting. Like, if you started with little k as a finite field, then for which n and d does there exist a polynomial of degree, for which n does there exist a polynomial of degree n in homogeneous and in variables, so x0 through xn minus 1, so on pn minus 1. Right, exactly. So you should give examples of CR fields K such that K of T is not CR. I mean, from the Tsen-Lang theorem, K of T is CR plus 1. That's what the Tsen-Lang theorem says. But K of T, there do exist fields K which are CR, but not such that K of T is not CR. Okay, that's a good, okay. Is CR plus n, but not CR plus n minus 1. I mean, it depends on how you come up with your counterexamples. I mean, there are counterexamples that you automatically get all of these things all at once. But I want to point out that, you know, it depends on the field K. I mean, if you take your field to be a finite field, then there are other theorems that I don't want to talk about, which say if you fix D and N, then it doesn't matter whether D and N satisfy one of these kinds of inequalities. If you let your finite field have enough elements, that's sufficient for there to exist a solution of every such polynomial. So I mean, for finite fields, something kind of interesting, a different interesting thing happens, which maybe I'll mention in just a second. But first, let me tell you why. Why do we consider these kinds of properties? I mean, it's fun, but it's also important. So there are applications to Brauer groups and Galois homology. And Galois homology and so what are they? Well, the first one is a very easy theorem, which says that every C1 field has trivial Brauer group. And because of that, has cohomological dimension 1. There are no higher Galois cohomologies of any finite Galois module. Finite meaning a set. As a set, it's a finite set with the Galois. So it's a finite abelian group with not finitely generated finite abelian group. Yeah, let me say this. So theorem 1, and these are in Serre's Galois homology book. So theorem 1, every C1 field K has trivial Brauer group. So the Brauer group of a finite field is trivial by Chevalley's theorem. So this is one theorem. And then this, I mean, well, it follows from this theorem 2, every C1 field has Galois cohomological dimension less than or equal to 1. What does this mean? So, i.e., if A is a finite commutative group scheme over K with Galois action, well, I mean, automatically it is a Galois action, then the higher cohomologies, the higher Galois cohomologies of A are 0. I mean, for I bigger than 1. So you have Galois cohomologies only for I less than or equal to 1. That's what it means to have cohomological dimension less than or equal to 1. And this, in fact, follows from this one by, just using Kummer sequences. But what is the proof of this one? So let me prove theorem 1. I mean, again, it's very easy. Proof of theorem 1. So the Brauer group, as you learned last week, that's the group of central simple algebras up to this equivalence relation, this Moridi equivalence, but every central simple algebra is equivalent to a division algebra. So let D be a finite dimensional division algebra with center A. So let this be a division algebra. So in particular, it's a vector space. And what's the dimension of this vector space? Well, that's pretty easy. If we base change to the separable closure, then this becomes a matrix algebra. So it's n by n matrices over the separable closure. So as a vector space, its dimension is n squared, because the dimension of the space of n by n matrices is n squared. So the dimension is n squared, where this integer n, it comes up so often we give it a name. So n is defined to be the index of D. So it's just the square root of the dimension as a vector space. Wait, did I already? Yeah, I guess I can use that one. And then there's, of course, another invariant. So, I mean, actually, you don't need this other invariant for what I'm about to do, but let me mention it because I'm going to talk about a generalization of this. So there's another invariant, so the index is one invariant, but there's another invariant, which is, well, we can take this division algebra, we can take its element, its equivalence class inside the Brauer group of this field. This is a torsion group. Every element has finite order, so we define the period of D is defined to be the order of this element in this group. So it's the least integer n such that when you multiply that element of the group by n, then you get 0. This is, again, a torsion abelian. So we have these two invariants, the period and the index. I actually only need the index for what I'm about to do. The point is that this is a Galois twist of the space of matrices. So we could ask, are there any interesting polynomials on this D? And that's the same as asking whether there are interesting Galois invariant polynomials on the matrices. The Galois group acts by conjugation. So the Galois group of K acts by conjugation on the space of matrices. So what is a homogeneous polynomial on the space of matrices that is invariant under conjugation? Wait, did somebody say something? There's the determinant. Yeah, exactly. Determinant. This is homogeneous of degree E, of degree n. And Galois invariant, so it defines, a polynomial on the division algebra called the reduced norm. So we get this map from D to K. It's a homogeneous polynomial map. And called the reduced norm. So the dimension of D is n squared. The degree is n. So unless n is equal to 1, n squared is bigger than or equal to n. So if n is not 1, then, so this is a homogeneous, I should have called this D. Sorry, let me call this D. Then I have to, okay, let me not call it D. I apologize, this is a different n than we had before. I mean, we have a homogeneous polynomial of degree n in n squared variables. So on projective space, Pn squared minus 1. So the reduced norm. So then reduced norm satisfies the C1 condition. So what was the C1 condition? It was that the number of variables, which in this case is n squared, should be strictly larger than the degree. I mean, before we were counting variables starting with x0, so the total number of variables was n plus 1. So it should be strictly larger than the degree, which is n. And if n is bigger than 1, then n squared is certainly strictly larger than n. So it satisfies the C1 condition. So if this is defined over a C1 field, then there's a solution. I mean, there's an element in the division algebra whose reduced norm is 0. But when you pass to the separable closure, it's a matrix. I mean, that's an element in the division algebra whose image inside the space of matrices is a matrix with determinant 0. So it's certainly not invertible. But a division algebra, every non-zero element is invertible. I mean, we have a non-trivial solution, so an element different than 0 whose determinant is 0, which means it can't be invertible. So this is a contradiction. So that proves that n has to be equal to 1. So n equals 1. So if you have any division algebra, then it's just the field K. So that proves that first theorem. And that second theorem follows. And using spectral sequences, you can get an analog of this theorem, which says that if you take a function field over a field K, then the cohomological dimension grows by at most the transcendence degree. So using spectral. So a consequence of this, again, this is in Serre's Galois cohomology. If K has cohomological dimension less than or equal to A, and capital K over little k is a finitely generated extension of transcendence degree R, or let me say n, I think is what I was using before, transcendence degree n, then the cohomological dimension of K is less than or equal to A plus n. So very similar to this version of the Tsen-Lang theorem. And let me just point out, there's an open problem here, which is this property CR and this property of about bounded cohomological dimension satisfy the same sort of theorem. And you might expect from this something, which is an open problem. Does every CR field have cohomological dimension? Does every CR field have cohomological dimension less than or equal to R? R. So, I mean, of course, that's what we just proved when R is equal to 1. And they both satisfy this kind of theorem, but not every CR field is obtained from a C1 field by this operation. So it's not clear. So this, as far as I'm aware, in Serre's book, he lists this as an open problem. So I think this is still open. I've only got a few minutes left, and I think what I want to do is just set up what I'm going to talk about for the next lecture, which is, let me see where I am. Well, let me talk about this a little bit more. So, I mean, we've seen two results that have sort of the same flavor. That when you go from when you go from one field to a transcendental extension, something changes in a certain way. There's another thing you could consider. I mean, so this was a theorem about the Brauer group, what I'm erasing right now, but it's not going to be true if you consider C2 fields that the Brauer group is trivial. So that's a good exercise. I mean, similar to that other exercise is exercise. Give a C2 field with untrivial Brauer group. And I mean, you could even consider the simplest kind of C2 field that we've seen so far would be you take two transcendental elements and you enjoin to K. So what is the Brauer group? Or not what is the Brauer group, but is this 0? I mean, is this the trivial group or not? So again, these kinds of theorems tend to be sharp in the sense that you can prove that if you take something this general, you can't prove this with an a plus n minus 1 here. But there's another way of generalizing. Instead of generalizing with cohomological dimension, we could ask about the relation between the period and the index. So let me just mention this conjecture, which if you want to read more about this, you should read in a paper by Colliot-Tsen that's on his webpage about Brauer groups. So I'm not sure that this is due to Colliot-Tsen. It's just a reference for this conjecture. So the conjecture is the following. Let K over little k be a function field of transcendence degree n over an algebraically closed field. Then, and let D be a division algebra. There are these two invariants associated to the division algebra, which I probably erased them. I mean, there's the period, which is the order of D in the Brauer group of K. So let this be a division algebra with over K, with center equal to K. And there's also the index, which is the square root of the dimension. So D is, when you base change to the separable closure, it's a matrix algebra, n by n matrices, and the index is just that integer n. And so one consequence of Tsen's theorem is that if you consider the case when, let me call this R, when R is equal to 1, then the Brauer group is trivial. Well, there are some things known about this period in the index. They have the same prime divisors. They're integers. They have the same prime divisors. The period always divides the index. They have the same prime divisors, so the index divides some power of the period. And the question is, what power? So the conjecture is that the index of D divides the period of D to the R minus 1. So when R is equal to 1, this says the index divides 1, which says every division algebra is index 1, and that's exactly what we proved in that theorem. When R is equal to 2, this says the index divides the period, but also it's always true that the period divides the index. So this is conjecture. The conjecture. But what's not is that the period and the index have the same prime divisors. Prime divisors. And also, this is one thing that's known. The other thing that's known is that the period divides the index. I mean, this is easy. If you take the index, you can find a splitting field of degree equal to the index. And then by co-restriction, it follows that the period divides the index. So the question is, what power of the period does the index divide? So R equals 1, R equals 1. This is that theorem we just proved, which is often called Tsen's theorem. I mean, even though it's a consequence of Tsen's theorem, this says that the Brauer group of a function field of a curve is trivial. But then R equals 2, this is a theorem of Johann de Jong. So de Jong proved that if you have a division algebra over the function field of a surface, so D over the function field of a surface, then the period equals the index. And in the third lecture, I'll show you a proof of this. I mean, there's a way of thinking about this in terms of things related to CR fields, things like that I'll talk about next time. But then when R is bigger than 2, this is open. So this is kind of an interesting problem, just to understand the Brauer groups, something about the Brauer groups of function fields. So I'm over time. Tomorrow I'm going to talk about, if you look at these kinds of fields we've been considering, function fields, and try to generalize the type of varieties that have points. So not just hypersurfaces, which are very special among all varieties, but more general varieties, what can you put there? And it turns out there's a very nice answer. And then on Wednesday's lecture, I'll talk about, well, what if instead of looking at function fields of curves, you look at function fields of surfaces, like come up in de Jong's theorem. And then again, I mean, we have this Tsen-Lang inequality, n should be bigger than or equal to d squared. So if you look at those hypersurfaces, what's the generalization of those hypersurfaces, and how do you use that generalization to prove de Jong's theorem? So that's what I'll do in the next 2 lectures.